Hello and welcome back to another video of Calc Nerd. So today's video is going to be on a version of Lights Out, which was originally made by Tiger Electronics. It's a fun handheld game. The goal is to get all the lights off, and some are randomly placed as on, and if you turn one on, it affects the ones around it. And it's actually a really fun game. So let me show you what Lights Out is on the calculator and how you can program it for yourself. Okay, now let me run program light out so you can see what it does. So it's going to first draw the board. I use X's and O's. X's represent lights that are off and O's represent lights that are on. It's going to give you a menu here. You can either play, edit, or exit. So I'm going to edit just to show you. I did make a level editor for Lights Out, which I think is kind of neat because it allows you to create unique levels. So let's say I want to turn this light on right here because it starts off with everything off. So I just click enter and it turns that light on. So as you can see, I can move over it and everything and it still works. And you can turn as many or as little lights on as you want. Just for the demonstration, I'm going to make a plus. And then I'm going to put just a couple down here. Okay, and then when you're ready and you have your custom level built, all you have to do is click clear. It will get rid of where your cursor is, and now you're in the actual game. So I'm actually playing right now. So whenever you make a level, it allows you to play that level right afterwards. And if you don't go to the edit and you just go to play, it randomly places lights, just so you don't have to make a level every time if you don't want to. So as you can see, my cursor is in the middle of these four lights right here, and there's also one in the middle. So with Lights Out, basically, wherever you are, I'm just going to call them pixels. So the pixel that you're on top of, it changes the state. If it's on, it becomes off. If it's off, it becomes on. And it does that for all of the four around it. So the one above, the one below, the one to the left, and the one to the right. So if I click enter to change that state of that key, it changed all of those to off. Now if I go here, for example, the one above is on, so it's going to be off. The one over here to the left is on, so it's going to become off. The one below is off, so it's going to become on. The one to the right is off, so it's going to become on. And the one that I'm on top of is off, so it's going to become on. And that's how the game logic works. And if I click it again, it brings it back to its original state. So it's a pretty fun game. Basically, the objective then is to get all the lights off in the end, and we'll see if I can solve it. Almost, but there actually is methods that work every time. If you want to learn those, I recommend just doing a little bit of research, but I find it's more enjoyable to try creating your own solutions and seeing if you can turn all the lights off. Okay, now let me show you how you can program or make program light out on your own calculator. So we're going to start off with a clear home to get rid of anything that might be on your home screen, such as math or other games or pretty much anything. Clear home is very oftenly used as a first line in many TI basic programs, just in case that there is stuff on the home screen. Del var matrix A, 8, 15 store into the dimensions of matrix A. For y, 1, 8, for x, 2, 12. So this for loop right here, these two for loops actually. So what it's going to do is y is just like the y on a graph and x is just like the x. So it's going to start off with the y value of 1, which is kind of backwards. The top here is 1 and it grows to 8 as you go further down the screen. So it's going to start at 1 and then x for x, 2, 12. So the first for loop is only going to increase when x reaches 12. So it's going to be for y, 1, 8. So x is then going to go to 12, and then it's going to bump the y up to 2, and then x is going to reach 12, y is going to be 3, and it's going to do that until y is 8. Output at y, x, quote a minus sign. output at y comma 13 comma quote a bracket, and output at y comma 1 comma quote another bracket. And that bracket right there is the reason that I don't start x out at 1, because I like the border on there. I think it makes it look nice. Output at y comma 15 comma sub light out, which you see on this side of the screen. It's just kind of something to fill the space, and it gives the name of the game. So comma y comma 1. If y is not equal to 1 multiplied by y is not equal to 8, then if not f part of x divided by 2, then output at y comma x comma quote an x. 1 stored in matrix A at y comma x plus 1. And 4 ends right there to end the 2 if-then loops, and then also the 2 for loops. And then this is where the menu comes in. So we just finished drawing the screen, and now we're at the menu that pops up, which asks if you want to play, create a level, or edit, and then exit. So menu quote light out, comma quote play, comma 1, comma quote edit, comma 2, comma quote edit, exit, comma 3. Label 1, so if you just play, it's going to do random integers, and I use k just so I don't have to use another variable. It makes it more efficient. So random at 5, comma 10 store into k, and what that is accomplishing is it's going to take somewhere between 5 and 10 lights that it's going to turn on, and then that's how I establish that. And then I also do the random position with the 2 comma 7 and 1 comma 6 here. And then after you do all that random integer stuff, 2 store into matrix A at y comma x plus 1. Output at y comma x comma quote and o. And you can also do a 0 if you would like. It's up to you, whatever your personal preference is. And then label 4, the reason I have a label 4 here is because when you create a level and then you want to play it, you don't want it to do that game loop where it puts randomly stuff on. You want to just start it when it'd be a blank screen if you didn't do that random stuff, but it's probably not because you made a level. So that's where the label 4 comes in. 2 store into y and 2 store into x. Repeat until k is equal to 45. Get key store into k. If sum of k is equal to the list of 24, 25, 26, 34, 105. So basically it's saying if the key, because get key is stored into k, so if the key is equal to 24, 25, 26, 34, or 105, then, so it's going to run until it reaches an end. Output at y comma x comma sub, xo, quote xo, comma 1 plus matrix A at y comma x plus 1 is equal to 2, comma 1. So matrix A at y comma x plus 1 is where it's checking, and it's checking to see if it's equal to 2. If it is equal to 2, that means this statement is true, and according to Boolean logic, that means it's a 1. If it's false, it's a 0. So we're automatically assuming that it's a 1, which would be the x, or assuming that it's off, and if it is equal to on, which is where the 2 comes in, then I'm adding 1 plus 1 because the statement is true, which would give us the O. That is an example of a simple optimization that TI Basic does. It assumes one thing if there's like 2 variables like that, and then it sees for the second one to see if it's also true. So yeah, that's just kind of an example of one thing. Max 2, comma min 12, comma x plus 2 times k is equal to 26, minus 2 multiplied by k is equal to 24 stored into x. The reason I have it multiplied by 2 is because there's a gap in between each of the x ones. I do that because it does look just a little bit nicer and it takes a little bit more room up on the screen. Max 2, comma min 7, comma y plus k is equal to 34, minus k is equal to 25, store into y. Output at y, comma x, comma quote a plus. If k is equal to 105, then for a, comma y minus 1, comma y plus 1, so for whatever a is, or sorry, whatever y is, y minus 1 and y plus 1, matrix A at a, comma x plus 1. If a is not equal to 1 multiplied by a is not equal to 8, then, so basically just making sure that it's not going to go up off the screen. That's what that line is doing. 2 minus 1 multiplied by answer is equal to 2, stored in the matrix A at a comma x plus 1. That's another example. I'm assuming that it's 2, and then I'm subtracting 1 if the answer is already equal to 2. So I'm assuming that it's on, and if it's off, if it's already on, then it's subtracting 1 because it needs to be turned off. That's what that line is doing right there. And then output at a comma x comma sub quote xo comma 1 plus answer is equal to 2 comma 1 and 2 ends. And then I'm going to do the same thing but for the x values. For a comma x minus 1 comma x plus 1, 2 multiplied by a minus x stored into k, matrix A at y comma x plus k plus 1. If a is not equal to x, then if a is not equal to 1 multiplied by a is not equal to 13, then 2 minus 1 multiplied by answer is equal to 2, stored in matrix A at y comma x plus k plus 1. Output at y comma x plus k comma sub quote xo comma 1 plus answer is equal to 2 comma 1. And then we have quite a few ends here, as you can see. There's 1, 2, 3, 4, 5, 6 of them. Go to 3 and label 2. 2 store in x, answer store into y. Repeat until k is equal to 45. Get key store into k. If sum of k is equal to 24, comma 25, comma 26, comma 34, comma 105, then output at y comma x comma sub quote xo comma matrix A at y comma x plus 1 comma 1. Min 12 comma max 2, x plus k is equal to 26. K is equal to 26 right here, and it's 2 times that. Minus k is equal to 24 and 2 times that as well. Store into x. Min 7 comma max 2 comma y plus k is equal to 34 minus k is equal to 25. Store into y. And the reason there is a 2 in front of these and not a 2 in front of these is because, again, I have a space in between each of the columns, but not in between each of the rows, because the space will not allow for that in the y. Output at y comma x comma quote a plus. If k is equal to 105, then matrix A at y comma x plus 1. 2 minus 1 multiplied by answer is equal to 2. Store in a matrix A at y comma x plus 1. End. 3 ends right there. Output at y comma x comma sub quote xo comma matrix A at y comma x plus 1 comma 1. Go to 4 and label 3. And that is the end of the program. So it's a relatively short program, and it's a really fun game. I hope you did enjoy today's video. I hope you make Lightout, and I hope you have fun playing Lightout. It's a really fun game, so I do hope you enjoy that. Thank you for watching today's video. I hope you enjoy. So yeah, thank you for watching, and as always, I'll see you in the next one.